Hello everyone, I'm Yang Liu. Together with my colleague Sujay, I'm going to talk about our synthetic benchmarks for explainable machine learning research. The last decade has seen a boom in both machine learning research and its applications. Driven by the availability of large, high-quality datasets, as well as models such as neural networks, machine learning models are being used in a wide variety of high-stakes domains. As a result, understanding why they make certain decisions become more and more important. Although many machine learning model explainers have been proposed, there hasn't been a widely used set of datasets and metrics for comparing explainers fairly. The goal of our work is to build such a benchmark suite for comparing explainers. Many different methods for explainability are being actively explored. In this work, we focus on the most common type of explainers, which are post-hoc local feature attribution explainers. So what are they? Let's start by assuming that we have a typical machine learning setup where we have a four-dimensional dataset and we have a trained black box machine learning model, fx, on the dataset. And now we have a four-dimensional data point x star that we want to predict. And passing x star to the model will yield a prediction y star. The goal of our explainer G is to explain why the model F makes its prediction given this particular data point x star. We need both the original data point x star and the machine learning model prediction y star, as well as information from the dataset to produce a list of feature importance weights, which correspond to how each feature contributes to the model's prediction y star. But how do we evaluate how good the feature weights are? Let's say we want to evaluate weight 1, and ideally we want to remove feature 1 and measure how much the prediction changes. But in reality, most machine learning models cannot handle arbitrary missing values. To address this, we compute the expected value instead. To compute an effect of removing a feature from one of the full feature set, we now draw feature 1 from conditional dataset distribution, where the rest of the features equal to the current data point value x star. However, even with this formulation, a big problem is that for most real datasets, it's difficult to estimate conditional distributions. Two approximations are often used to make computing this feasible. First of all, one can assume feature independence. Then instead of sampling from the conditional distribution, you can sample from the marginal distribution. Second, one can further assume that the model is linear. Basically, now you could get away with finding the empirical marginal mean of feature 1 and plug it in to compute the effect of ablating that feature. But the big caveat is that the two assumptions rarely hold. It is common that features are correlated and models are nonlinear. To address this, we propose to use synthetic datasets where you could directly sample all the conditional feature distributions to compute the effects of feature ablation. As an example, one could choose multivariate Gaussian that is defined by the mean vector mu and covariance matrix sigma. In this talk, we'll set mu to a vector of 0 and use the rho to control the feature correlation. After generating features, we have three types of functions to generate labels. They are linear, nonlinear additive, and piecewise constant. Now that we have the datasets, we define a few metrics to evaluate how good the weights are. Let's assume the absolute values of the weights are decreasing. We first define faithfulness minus by evaluating the model 4 times with one feature removed each time, and compute the correlation between absolute weight and the absolute effect of the single feature removal on the ML model's output. We could also define faithfulness plus by including only one feature at a time. Similarly, when we gradually include features from least important to most important and compare whether the effect sizes monotonically increase, we could define monotonicity minus. And we can also define monotonicity plus in the opposite direction. In the paper, we continue to define 6 more metrics, including ROR-based metrics that involves removing features and retraining machine learning models, and Shapley value-based metrics that measure how much the feature weights agree with Shapley values. It is noteworthy that given a d-dimensional dataset, Shapley value-based metrics require 2 to the d model evaluations, which could quickly become computationally prohibitive. The full XAI bench has 4 main components: a set of data generator, machine learning models such as neural nets and decision trees, implementations of several explainers, and a set of metrics. Now my colleague Sujay will tell you about the experimental findings.
Thanks, Yang. Hi everyone, I'm Sujay and I'll be walking you through some of our experimental findings. Firstly, we benchmark explainer performance under feature independence. We run experiments using the normalized multivariate Gaussian dataset with zero mean identity covariance matrix and piecewise constant labels. If we look at the Shapley correlation metric, SHAP, brute force SHAP, SHAP-R and LIME offer accurate approximations of ground truth Shapley values. However, none of the explainers is able to outperform the random explainer on monotonicity minus, suggesting that this metric is not helpful for this dataset and model. As can be seen, the performance of explainers varies dramatically across metrics for a fixed decision tree model. Next, we compare the performance of the explainers as a function of feature correlation, which is controlled by varying rho, the non-diagonal term of the covariance matrix of the Gaussian dataset. It is evident that as the correlation among features increases, explainers become worse. Explainers like SHAP assume complete feature independence and therefore they perform well when features are indeed independent, that is rho equals 0 in this plot. However, its performance degrades as rho increases. Furthermore, we demonstrate the power and flexibility of our synthetic datasets by simulating the popular wine dataset with synthetic features so that it can be used to efficiently benchmark feature attribution methods. This dataset has 11 continuous features and a target quality rating. To simulate, we compute the empirical covariance matrix, which is then used as the input covariance matrix to generate synthetic multivariate Gaussian features. Simulated wine quality is labeled by a k-nearest neighbor model based on real data points. We train 3 models on both simulated and real wine datasets and compare the mean squared error of explanations on a common held out real test set. Consistent low mean squared error across ML models and explainers suggests that the simulated dataset is a good proxy for the original wine dataset for evaluating explainers. Based on this, we benchmark 5 explainers on the synthetic wine dataset. Here, SHAP performs well on the Shapley metrics, which is consistent with our previous results. This example shows how our library can be used to benchmark various explainers on a real-world dataset. Through our experiments, we gave a sample of the types of experiments that can be done using XAI Bench. For researchers looking to develop new explainability techniques, we recommend benchmarking new algorithms across all the evaluation metrics using our synthetic datasets. For researchers with a dataset and application in mind, we recommend converting the dataset into a synthetic dataset as we show for the wine dataset. This gives us the ability to evaluate explainability techniques on perturbations of the original covariance matrix to simulate robustness to distribution shifts. Finally, researchers can decide on the evaluation metric that is most suitable for the application at hand based on model, intended use case, size of the dataset, and level of feature correlation. For example, ROR-based metrics may be the most appropriate for structured data that is prone to unreliable function evaluations in low-density regions of the feature space. In conclusion, XAI Bench releases a set of synthetic datasets along with a library for benchmarking feature attribution algorithms across 10 evaluation metrics. Thank you.